Streaming, very good. Okay. So are there any questions about the homework assignment? Some people have turned it in already, other people are well on track, okay, in progress doing it, so that's all very good, encouraging. Are there any specific questions about that homework assignment? No? Okay, so it might take you a few iterations to get it done to the point where you go like, I'm really happy with this answer, or I cannot find any other way to make it better. You don't have to optimize it, by the way, okay? If you run out of time, you got other homework assignments to do, you can just say, okay, it's working, it's good, I'm gonna turn it in, just make sure it meets all the requirements according to the homework assignment, okay? So that's one thing you might wanna double check before you turn it in, okay? Like the labeling of the pins, stuff like that, okay? If then, yeah, go ahead.
Oh, I have a slightly unrelated question.
Go ahead.
Monday is Labor Day. I
Yes.
just wanted to confirm that we didn't have class.
No, we do not have class on Monday, so any due date that falls on Monday, I'm gonna put it to the first moment of Tuesday.
Okay, so that the assignment's going to be due
Yeah,
Tuesday.
yeah, like first thing on Tuesday. Midnight.
Oh.
Yeah.
So 11:59 Monday.
No.
12.
0 hour on Tuesday.
Okay.
Yep. So technically it is on Tuesday.
Okay.
Yep.
So 11:59, 59.9 bar.
Yeah, that would still be on Monday, right? That would still be on Monday.
Well, the mathematical equivalence.
Yep.
It's close.
Close enough, yes. All right. So we talked about addition, we talked about subtraction. Are there any questions about addition and subtraction, the way we have discussed these particular topics? Yeah.
Couldn't you, with a single gate, make the 3x3 adder that we have created into a subtractor?
Into a subtractor?
Or so
not using a single gate, because the calculation of the t terms would still require that you splice out all the p's and the g's and combine those things with k0 and combine the conjunctions with a big disjunction.
But it's the same format. I'm saying, if you could use that single gate to flip whether or not
That would be correct.
How?
Yes.
Yeah.
So if you did it right using the adder, when you do the adder, you do it right. You only need to flip two things in the design to turn it into a subtractor. And then you have to relabel the pins a little bit, because instead of having a carry in, you have a borrow in. But other than that, the subtractor is the same as an adder. You just have to make two minor changes. But if you do it in a slightly different way, then there will be a little bit more stuff to do, a little bit more to modify. But nonetheless, it is not difficult to turn an adder into a subtractor.
Like, could you make it so that just by adding a single input, I guess, you could flip it at will?
Yeah, you could. I can see how that can happen. Yeah. Mm-hmm. Yep. All right. So any other questions related to addition or subtraction? Okay, no questions. All right. Well, I have a question. Okay, let's go ahead and take a look at an example, and then we'll use that as a starting point for today's class. I'm going to use my document camera here. Okay, that's coming kind of handy. Okay, we want it to go a little bit like that. Maybe. Okay, accurate enough? Good enough. All right, so what we want to do is to figure out, okay, what is this? And of course, we're dealing with binary numbers here. What is 000 as a binary number minus 0001 as a binary number? Now, let's not think about the values they're representing. So what we want to do is to blindly go through the mechanical stuff, all the gates, all the logic, to do this calculation, but not really to worry about what are these things representing. Okay, so the typical way that I do this is I have a row for the Qs, just to match up with the discussion that we already have. This will be the T row because they're the borrows. And then we have a B0, which is assumed to be 0 in this case because we have a specific subtraction, so we can assume that there's no borrow. So to do this, we have 0 minus 1 being a 1, and with a borrow, 1 minus 0 is a 1. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow. So the answer is we have an answer of 1111 as a base 2 number and a borrow out in this case as the leftover borrow. Is that okay? Does everybody understand this part? Okay, this is how we set up the adder, and this is also going to be how we set up the subtractor. Is that okay? Okay, just mechanically, when we look at the gate logic and how we apply the R function, the result function, and how we apply the B function, the borrow function, this is the result. But then it doesn't seem to make a whole lot of sense, does it? Because 0000 has 4 bits. Usually is representing the quantity of 0. 0001 as a binary bit pattern is usually used to represent the quantity of 1. 1111 is the quantity specifying 15. Okay, but it makes sense in a certain way because we have an overall borrow. That borrow is borrowing 1 from the 16ths. So when you look at, oh, okay, so we are borrowing a 16 and then we end up with 15. That means I have $15 in my pocket, but then I have one little card of reminder that I owe somebody $16. So my net worth is 15 minus 16, which is -1. Okay, my net worth is -$1, which is correct because 0 minus 1 is in fact -1. But this is a really awkward way to represent -1. Is that okay? Okay, so we're starting with this little discussion, and then we move forward. Okay, I'm going to go to the notes here so that you know where to find it. It is called signed value representation, and it has got a lot of stuff here, arithmetic negation and stuff like that. Okay, and then we jump to the number circle. So what I want to do is kind of change the ordering a little bit. So I'll start to talk about the number circle first. Now, I didn't have enough time to draw the pictures and include it in my notes, and that's why it's a little bit dry and boring. But I can make it up by using my document camera, so I can draw all those pictures now, and they will all be recorded. Doesn't hurt to double check, make sure my recorder is on with sounds, right? So we want to look at my OBS show. Yep, so sound is good. It is streaming already, so that's good. Yeah, I'm not recording on using OBS. I'm just streaming, so it's all being uploaded, live. That's all good. Okay, so now what we want to do is to look at the number line, and then we will switch from a number line to a number circle. Okay, number line concept is, you should know that already. You have a 0, 1, 2 on one side, -1, -2 on the other side. And when you take your math classes, the professor will tell you that the number line goes indefinitely on both sides, right? Because when you look at all the possible integers, there's no end to it. If somebody claims and say that, hey, look at this, x here is the largest integer, or the integer with the largest value, then my question is, what is that plus 1? And that's why it never ends, right? But then in your C++ programming classes, or just about any programming classes, you learn that integers can they have a very specific range. You cannot store values beyond a certain range given a particular width for integer representation. So did you guys learn that in CISP 360, or that concept was never discussed? Okay, it's all good? Okay. So with 32 bits, we can handle plus and minus 2 billion or so, okay, a little bit more than 2 billion. With 64-bit, no?
What's that to the power?
Yeah, 2 to the power of 31 on kind of both sides. So that comes to around 2 billion something. 64-bit numbers can go quite a bit more, but nonetheless, there's still a limit, okay? So what we want to do today in this class is not to deal with 2 to the power of 32 or even 16. We're going to deal with 2 to the power of 4, where things can be easily visualized, okay? So that means when you are using integers in the setting of using a processor to add, subtract, and whatnot, you are not dealing with a number line that goes indefinitely on both sides. We're dealing with a number line that has a beginning and it has an end. So 0 is here. If we're dealing with 4 bits, then you're looking at, okay, let's say that's 8. Okay, I think I messed up. Let's do it one more time.
It's 4 bits on each side of 0.
Yep, so 4, 8, 16. There we go. There we go. Okay, so we have 16. So we have 1, 2, 3, 4, 5, 6, 7. On one side, -1, -2, -3, -4, -5, -6, -7, and -8 on the other side. If you're dealing with a 4-bit integer, these are the values that you can represent using a 4-bit integer signed. Okay. Now I didn't say anything about the bit patterns. I'm simply saying that yes, they can represent these particular values, but which bit pattern is representing which value, I haven't got to that part yet. Is that okay? All right. Okay. So at this point, I want you to change your view of a number line into a number circle. In other words, we take the 2 ends of this number line, and then we draw a circle. We connect those and turn it into a circle. Okay. So let's see what a circle would look like in this case. All right. So we'll draw a circle. I just have to make sure my circle is small enough so it fit in the entire screen. This is 0. I like base 2 numbers because you can just keep dividing by 2. You know, base 10 is hard because you can do the divide by 2 and then you have to divide by 5. I mean, it's pretty hard to space out 5, correctly, but dividing and putting the midpoint into something is always easy. Okay, so we have 0, 1, 2, 3, 4, 5, 6, 7. We have 8 non-negative values. Then we have -1, -2, -3, -4, -5, -6, -7, and -8 as negative values. So half the wheel are non-negative numbers and half the wheel are negative numbers. Is that okay? Okay. So now we start to think about, what about the binary representation of these specific values? Okay, so we'll start with 0 because 0 seems to be a good starting point. As a 4-bit number, what do you think would be a good bit pattern to represent 0? Okay, that seems to be a pretty natural choice. 0, 0, 0, 1, 0, 0, 1, 0. Is that okay? 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. Okay, cool. So far, so good. Because if you apply base conversion, 0, 1, 0, 1 is exactly 5. Because it has 1, 1, it has 0, 2, it has 1, 4, and it has 0, 8. So when you add up those things, you have exactly 5. Okay? What about -1? Well, let's just continue this bit pattern thing. The next one is going to be 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. Okay. That is one way to look at signed values, or values that can be negative, but represented only using zeros and ones. Okay? But I have a problem right away. Okay? Because isn't this thing also known as 8? Because it is 1 times 2 to the power of 3. Yeah, that's known as 9, 10, 11, 12, 13, 14, and 15. Okay, so now we have a big, huge confusion here, because according to this picture, 1101 can be interpreted as -3, but it can also be interpreted as 13. Which one is it going to be?
Who decides?
Who cares? Why do you care?
It's got two, like these numbers are two things behind the scenes.
Yeah, but why do you care? That's the question. Why are we getting confused over something that we should not be getting confused over? What are you talking about, Tak? You know, what do you mean by what do we care about whether 1101 is representing -3 or 13 as a value? Well, I'll tell you why. What is 13 minus 2? Okay, it's 11. Okay, fine. What is -3 minus 2? Is -5, right? Okay, fine. What is 1101 as a base 2 number minus 0010? Well, let's figure it out. Okay, so we'll do the full version. Okay. Okay, 1 minus 0 is a 1. 1 minus 0 is a 1. 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. 1 minus 0 is a 1. 1 minus 1 is 0. Neither has a borrow. 1 minus 0 is a 1. 1 minus 0 is a 0. Wait, hold on. There's a 1 here, sorry. Okay. 1 minus 0 is a 1, not a 0. Okay, there we go. Okay, that seems to be, oh, I see. Okay, let me move that a little bit. Okay, there we go. It's 1011, but if you choose to interpret 1101 as 13, this is correct because it is representing 11. If you chose to look at 1101 as -3, it works too because this is -5. That is why I asked the earlier question, what do you care? It makes no difference. Addition continues to work, subtraction continues to work. What do you care? Is that making any sense? It seems really counterintuitive because at the moment we introduce this thing, go like, oh, so one particular bit pattern can have different interpretations. But then it doesn't really matter because the mechanism that we use for adding and subtracting in binary is not sensitive. It is not sensitive at all to the interpretation either way, which is great. The only time you really care is when you compare. Okay, so let me use another slide here. We'll get back to this wheel. So I'm going to tear this page out because we're going to use it again. So the only time it really matters whether a particular bit pattern is representing a particular value or the other interpretation is something like this. So here's 0, 0, 0, 0, 0 as a base 2 number. And my question is this. Question mark. Is 0, 0, 0, 0 base 2 less than 1, 1, 1, 1 base 2? Now it matters. Because if you choose to look at 1, 1, 1, 1 as the representation of -1, then the answer is false. If you choose to look at 1, 1, 1, 1 and say it is representing 15, then the answer is true. So only when you compare, then it matters whether it is representing a signed value or an unsigned value. 1111 as an unsigned value represents 15. As a signed value, it represents -1. Is that okay?
Sure.
Okay.
Where's the sign?
Sorry.
Yep.
You said sign is -15.
Signed is -1.
-1. Sorry.
Yep. Unsigned is 15.
Got it.
Mm-hmm.
The unsigned generally means above 0, or greater than 0. Or
At
0
least
or
0, 0 or more.
Yeah.
So when you use the word unsigned in C or C++, it means you are not representing negative values. When you use int by itself, it is by default signed. Now you can always say signed in front of an int, but it's redundant. It's always signed to begin with by default. Okay. So are we doing okay so far with these concepts? Signed or not does not matter until you compare. That is the only time you have to say, okay, how should we interpret this particular bit pattern? But if you're just adding, hey, doesn't really matter. If you're subtracting, it doesn't matter either. It's only when you compare, then it starts to matter. All right? So now we have a different question now. The other question is, how do we flip the sign of a number?
Where's it stored? Where's the sign stored?
Well, the sign itself is not quote unquote stored anywhere, but there's an indicator whether the number is negative or not. Okay, so you look at 0001, it's representing 1. Now, if we fix with the signed interpretation, then 1111 is representing the negation of that, the arithmetic negation of that. Is that okay? When you look at 0010, which is representing the value of 2, can anyone guess what is the binary representation of -2? 1110, and we know that because of the number wheel. We look at the number wheel, we go like -2 has a representation of 1110. Okay, so it's 1110 is representing -2. So now the question is, can I derive a binary bitwise operation to flip the sign of a number? Given the number is represented as a binary number, can I figure out a bitwise operation that can flip the sign of a particular number? Give me 5. I will tell you what -5 should be represented. Something like that. Well, we are using 4-bit as an example, because I hate writing like 20 gazillion ones. Yep.
Isn't it like you subtract one and then flip all of the...
Okay, you're right. Okay, so the number wheel is actually helpful to find out how to get it done. So I'm going to put the number wheel back on. Do you notice anything about the bit patterns from 1111 all the way down to 1000? What happens when you subtract the signed value from the unsigned value? What do you get? You get 16 in every single case. 15 minus -1 is 16. 14 minus -2 is 16. 13 minus -3 is 16. Okay? Okay, so what do you think you can do to do this conversion? So let's look at it from the arithmetic perspective, okay? So let me use, I can use this area here. Okay, so if you look at, okay, let's say X is a bit pattern. It's a 4-bit pattern. Okay? So what X can be is any one of these, okay? What is 16 minus X? That is the question. Let's take a look. 16 minus 2, this is 2. 16 minus 2 is which bit pattern?
Or 16 minus 2.
16 minus 2. Now 16 minus 2 is 14, right? And 14 has a bit pattern of that. Okay. But it also has an interpretation of negative 2. Okay, cool. What about 16 minus 11? 16 minus 11 is 16 minus this particular bit pattern. But we already know in base 10, right? 16 minus 11 is 5. 5 is over here. Hey, but this bit pattern is also representing negative 5. Okay, are we starting to notice a pattern? 16 for 4-bit numbers. 16 minus x will give you the bit pattern of the arithmetic negation of x. Okay, let me write it down. Is the arithmetic negation of x, or the representation thereof. And it works all the time. That is kind of cool, but we have one minor problem. Because when your processor is only 4-bit wide, you cannot represent 16.
So you need to borrow.
You need to, yeah, you need to spread out the 16 so that it can be expressed by 4-bit numbers. Okay, so let's see how we can do that. So 16 minus x is the same thing as 15 plus 1 minus x. Does anyone want to challenge that? No? Your math is good? Okay. Does anyone want to challenge this? I know I jumped a step, but would that be the same? I'm just putting things in different places, right? Associative property of addition. Is that good?
Yeah.
Okay. What about this one? Hold on a second here. Now we have to stop. Right?
What does that say?
Well, this is the tilde symbol. Okay. What does that mean in C and C++? Okay, so it means bitwise not. It's bitwise not.
So negate.
It's doing negation on a per bit basis. But how? I mean, we just changed from a arithmetic operation, 15 minus something, into a bitwise operation, which is the tilde symbol. How is that possible? Okay. What is 15 as a binary number? Okay, 15 in base 10 is 1, 1, 1, 1 as a base 2 number. Very good. So let's say x is represented as A, B, C, D as digits. Okay, so A, B, C, D are the digits of x in this case. What happens when you say 1, 1, 1, 1 minus A, B, C, D, where A, B, C, D, each one is an individual bit? What do you get? You go like, okay, we get 1 minus D, 1 minus C, 1 minus B, and 1 minus A as the result, right? There's no borrowing of any kind. The borrow is guaranteed to be 0 because the first number or the first value, the minuend, is a 1. So regardless of the subtrahend, the borrow is always going to be a 0. We know that part, right? So it's pretty easy. So we can look at this digit here and say this is just 1 minus D, this is 1 minus C, this is 1 minus B, and this one over here is 1 minus A. Okay, cool. But what do we know about A, B, C, D? They are all bits. They're all binary digits, which means A, B, C, D, each one can only be a 0 or 1. What happens when you have 1 minus 1? Come on. You get a 0, yes. What is 1 minus 0? You get a 1. Wait, hold on a second here. That means if A is a 1, 1 minus A is a 0. If A is a 0, then 1 minus A is a 1. Isn't that the same thing as negation? So this is why it is a bitwise negation. 15 minus a 4-bit number is bitwise not, bitwise negation for each position. that okay? Which is also known as 1's complement. So let me add to here. So 1's complement of x plus 1. Is that okay? So when you add 1 to 1's complement of a bit pattern, that entire operation is called 2's complement. Yep. So this whole thing is defined as 2's complement. I use C2 to represent 2's complement. So 2's complement of a particular bit pattern is nothing more than a bitwise knot plus 1. And here's the magic, okay? So the magic is I claim that this is the same thing as an arithmetic negation. Okay? Yep.
Wait, did you say 2's complement is just 1's complement plus 1?
Correct.
Okay.
Just like the way it is written here.
Okay, I should
So 2's complement of x is 1's complement of x plus 1.
Okay.
But 1's complement itself is nothing more than just a bitwise knot. In other words, you look at each individual bit of the representation of an integer and flip a 1 into 0, flip a 0 into 1 for each bit position. Are we okay so far? Okay? But the magic part is not this part here. The magical part is I claim, okay? So let me start with a new page because we are going to go through some examples on the new page. Okay, so TAC claims C2 of x is the same thing as arithmetic negation of x. They mean the same thing. Everything that you can do with arithmetic negation, I can do it with 2's complement. It would work out exactly the same way. All right? So that's a pretty big claim. Because, hey, 2's complement is easy to do. It's just a bitwise operation plus 1 addition, which we can do with transistors, right? But the negation, arithmetic negation of a value is conceptual, okay? You're basically saying, if something is going in that direction by a certain amount, I'm flipping it to go in the opposite direction by the same amount. So it's a concept. So what do we know about arithmetic negation itself? Okay, it is its own inverse, right? The negation of any value is the value itself. So if I claim that 2's complement is doing the same thing as arithmetic negation, it has to have this same property as well. That would make sense. So we want to check. So we say C2 of x, and you take another C2 of that, it should give x back to you. The question is, does it? What do you think? Maybe, maybe not. Let's try it. Okay, so we'll try it on certain patterns first. So of the entire number wheel, which one do you want to try? You guys can pick. You can pick the tricky ones like 0. You can try the other tricky one, which is -8. Or you can try something that's kind of more benign like 2 or -1. Your choice. Yep. 7? Okay, we'll try 7. So 7 has a bit pattern of 0, 1, 1, 1. So we'll go ahead and apply that here. 2's complement of 0, 1, 1, 1. Okay, so we'll write the entire thing out like that. So we'll solve the internal one first. So now we have the 1's complement of 0, 1, 1, 1 plus 1. Okay. 1's complement is to flip all the 0s to 1s and all the 1s to 0s. So now we have 1, 0, 0, 0 plus 1, right? And all of these are binary numbers. So now we have 1, 0, 0, 1, like so. So now we applied the outer 2's complement to 1, 0, 0, 1 as a binary number. So that becomes 1's complement of 1, 0, 0, 1 plus 1. And when you take the 2's complement of this thing, it is a bitwise knot. So all the 1s become 0s, and all the 0s become 1s. The whole thing plus 1 is 0, 1, 1, 1. Wow, that works. So the 2's complement of the 2's complement of a particular bit pattern is that bit pattern itself. Just like with arithmetic negation. Maybe it only works for non-negative values. Let's try something that's negative. You guys pick. -6. Okay. So when we look at the chart, okay, -6 is 1, 0, 1, 0. Okay. All right. So we'll apply the same thing. C2 of C2 of 1, 0, 1, 0 as a binary number is C2 of C1 of 1, 0, 1, 0 plus 1. And C1 is just bitwise NOT. We flip the bits, 0, 1, 0, 1 plus 1. And that becomes C2 of 0, 1, 1, 0. Okay? So far so good. Then we apply 2's complement to 0, 1, 1, 0, which is C1 of 0, 1, 1, 0 plus 1. And this is just flipping all the 0's to 1's and all the 1's to 0's. So it becomes 1, 0, 0, 1 plus 1. And we get 1, 0, 1, 0 back. Cool. That works. Well, let's throw some really tricky cases. Okay, you guys pick all the easy ones. Let's, huh? No. Well, 5-bit. If all the numbers are 5 bits, it still works out the same way. So we want to throw some boundary cases. Okay, boundary cases in this case, would be the 0 and the -8. Those are called the boundary cases because if you go one step further, it goes. Something is entirely different. The sign is entirely different, or it goes from negative to positive. Okay, so those are the boundary cases. We like to test with boundary cases. Okay, so let's try 0. So C2 of 0, 0, 0, 0. Okay, so let's figure out what this is going to be. So it becomes C2 of C1 of 0, 0, 0, 0 plus 1, right? And what is the 1's complement of 0, 0, 0, 0? You flip all the 0's to 1, so you get 1, 1, 1, 1 plus 1. And some of you may say, aha, tech, gotcha, okay? Because that is 16. But remember, we are limiting all our math to 4-bit wide calculations. 1, 1, 1, 1 plus 1 is 0, 0, 0, 0. What about that extra 1 at the very end? We don't track it. It goes away. We would have lost it, okay? That's what our carry flag is remembering. But the carry flag is not represented anywhere here. So now we only get this back. Then repeat the whole thing, right? It kind of works out. It is weird. All right, so that's one property of arithmetic negation, is it is its own inverse. But there are many functions where it is its own inverse, but they're not arithmetic negations. So just because it has this property doesn't mean that it is arithmetic negation. Okay, fine. So we'll test some other properties of arithmetic negation. Okay, so one other thing that we know about arithmetic negation is this. So we can say x minus y is really the same thing as x plus the negation of y. Would anyone challenge that claim? Okay, that's what you guys learned, right? Cool. So that means, if I claim that C2 or 2's complement is the same thing as arithmetic negation, then I could also be able to establish this. X minus y is the same thing as x plus the 2's complement of y. Right? Because I'm claiming that C2 is really the same thing as arithmetic negation. So that should hold.
It returns the negative one. It returns negative one. Whatever we're doing like coding speak, it's a function that returns negative one.
It returns the representation of the negation of y.
Yeah.
Yep. Okay, so what do you guys want to choose as X? What do you want to choose as Y? Now this time you have to be kind of careful because we have to remember the result has to be a value that can be represented in this wheel. So if you choose to say, oh, let's try -8 minus 1, it won't work because -9 is not on this wheel anyway. So you got to choose a little bit more carefully, make sure that the result is representable using this wheel. That's all. That's the only requirement. What do you want to do? I'm giving you guys too much degrees of freedom, huh? Makes it confusing. It's like, oh, no, we don't want questions. We want answers. We just want specific.
5, -6?
Or -13 plus, oh wait, it's positive and negative.
5 minus 6 will work, but -5 minus 6 will not. Because -5 minus 6 is 11. The 11 is not representable here.
We'll try that again.
8 and 13.
Huh?
8 and
8 won't work either. Because 8,
13. Oh, it's right there.
yeah, we have to use the sign interpretation.
Right.
So only the signed part can be used.
7.
Always use 7.
Anything? Come on.
I just moved, I shifted. That's all I did.
Okay, how about 2 minus 5?
That's what I was gonna say.
Okay, 2 minus 5. Okay, so let's try 2 minus 5. Okay, this is the base 10 representation. I'm just documenting what we want to do. So we look at this as, okay, so we can see this as 2 plus the negation of 5. Okay, now we convert everything to base 2. 0, 0, 1, 0 plus this 2's complement of -5. And I'm too lazy to figure it out, so I just look it up as 1, 0, 1, 1. Okay, let's. Nope. Nope, I just.
We're supposed to put a -5.
Yeah, there you go. Because this is the negation, which is C2. This is 5, which is 0, 1, 0, 1. That's it. Okay. All right, so let's work this out. 0, 0, 1, 0 plus C1 of 0, 1, 0, 1 plus 1. Okay, so this entire thing is the 2's complement. And we'll figure out the 2's complement first. We flip all the 1's to 0s, all the 0s to 1s, so this becomes 0, 1, 1, 0, 1, 0 plus 1. And that becomes 1, 0, 1, 1. Are we doing okay so far? Okay. So now we have to work out what is 0, 0, 1, 0 plus 1, 0, 1, 1. I'm going to do it in a vertical way over here. So 1, 0, 1, 1 plus 0, 0, 1, 0. There's a 0 here. 1 plus 0 is a 1. 1 plus 0 is a 1. That's a 0 with a carry. There's no carry here. 0 plus 0 is a 0. 0 plus 1 is a 1. There's no carry here. Okay, that's a 1. There's a 1 here. Seems correct to me. So we have 1, 1, 0, 1 over here. Okay. When we look up the number wheel, 1101 is representing -3. Is that the value that we are trying to get to? 2 minus 5 is -3. So it does work. Yep.
I have a question. You said that 11 was represented on the wheel, but we have it on the line.
Right, but you have to use the sign portion. So when we say that it has to be a value that is on the wheel, it has to be the inner circle that we are dealing with here. The outer part, which also repeats this portion, are only usable when you're dealing with unsigned numbers. Every time you deal with only signed values, it has to be within the inner circle. I'll try to avoid doing this too often because my small motion around this is amplified to big circles on the screen. Okay, so I got to tell you this joke. Well, not joke, it's an actual thing that happened. When I was a college student, that was a long time ago, back in the 80s, I took a class called file structure. And the file structure class is basically explaining how files are stored on the hard drive, like how the clusters are arranged and stuff like that. Kind of boring and dry topic because it's mostly just specification. There's not a whole lot of intellectual stuff in it. the professor who taught that class had a microphone, because he has a relatively soft voice, so he had to put on a mic, and it's amplified. But he also he's really monotonous. Okay, if I'm monotonous, he's like super monotonous. And when he's thinking about things, he would do this. He would go like, let me think about it. Of a class of 60, about 30 people would go to that class. So 30 people did not even bother to go to class. Of the 30 people who are physically in the class, about 15 can stay awake. And I'm amongst the first 4 to fall asleep. And I'm always sitting in the front row, and nobody is sitting here.
Professor ever embarrass you? Did they ever embarrass you?
The professor or the other classmates?
Either.
If he attempted, I did not notice.
Well, it's hypnotizing, isn't it? It's hypnotizing, isn't it?
It is very hypnotizing because the monotonous voice is one, the really boring subject matter is the other one, and then plus that, circular motion on the big screen, that's just the last thing that I need to fall asleep.
Or it's teaching through hypnosis. So you remember it all really, really well.
Well, he apparently he didn't even care whether people were falling asleep left and right or not. He just kept going. And this is back in the old days when, okay, this is the other part where it gets really boring. This is back in the days when people used overhead projectors. Okay, remember those old style overhead projectors where there's a light table, you slap a transparency on it. Okay, so he had everything pre-printed already. So he just slapped a transparency onto the projector and then started to teach out of it. So the class is either really crazy trying to copy everything onto their own notes, or falling asleep. And I have professors who did not just have sheets of these transparencies prepared, and back in those days they had rolls. So at the beginning of a class, it's kind of like film, so you would put in the roll, the roller onto that thing. So after talking about a certain idea, it's just scrolling like this to move on to the next one, right? So you can see the class frantically trying to catch the last part of what is being scrolled off the screen at the time. See, you guys don't have to deal with that. I mean, because I'm recording everything.
It's like PowerPoints are a pain.
Yeah, those are painful too.
If you aren't given it, if they don't give you the PowerPoints to study, then it's annoying to watch PowerPoints because you have to take notes constantly.
Yep, because PowerPoint presentations usually is just note to self, right? Yep.
Most people.
In my experience, university professors could not possibly care less whether you attend or not.
Exactly.
I had one professor, it was only like a 20-person class, and this was right before a break. I think it was Thanksgiving break, so a lot of people left early. I came into the lecture about 20 minutes late, and I was the only one in the lecture, and she had been lecturing for 20 minutes with not a single person in the room. She did not care even a little bit that there was no one there. She just continued lecturing as though there was.
Just did you remember that when it was time to hand in your
That
assignments? This is the level of ruthlessness this person will project.
No,
Well,
she
but
did
you
not.
have to remember that at universities, they have classes in auditoriums. So we are talking about, a class of 200, 300 students. So professors who are used to teaching those classes, they're just talking to air.
Yeah.
Because they can't even see the individual students.
Well, it's also intimidating. You don't want to see the individual students. You don't want to think about it as, oh, I'm trying to talk individually to 400 different people.
Oh, I beg to
Because
differ.
you
I like to
really
see the
care.
agonies of people going like, what are you talking about? Why do we not care about the sign of the number?
You did seem
A lot of them don't
particularly
like
pleased.
public speakers.
It's kind of the whole, that binary representation of 13 and negative 3 are the same. It's kind of like world bending. It's like, wow. But it's really cool to see that explode. That's just back and forth.
Yep.
It's really cool.
It's really helpful to kind of see it like this, as an actual examples. But everything comes from the equation that we had earlier. Let me see where I put that. Everything came from that 16 minus x is the representation of the negation of x. So it all stemmed from the observation that we had here. Okay. So are there any questions about sign representation or how you represent negative values but only using zeros and ones? Good questions? Okay. So one thing that we probably want to notice is one thing that is sort of important. It has to do with the sign of a particular value or the sign of a value represented in binary. If you look at all the negative values, what do you notice? What is common to all the negative values? The most significant digit is a 1. Yes. And that's why the most significant digit of a sign interpretation is also known as the sign bit. Okay? So that's the sign bit because it tells you if that bit is a 1. Okay, let me point out which one we are talking about. So we are talking about the first or the most significant bit. Now we are only dealing with 4 bits here, but you can probably imagine if I extend this to 64-bit, it's the same kind of pattern. Okay, the most significant bit, or bit 63, in the case of a 64-bit number, is the sign bit. If that bit is a 1, then the number is negative when you choose to interpret it as a signed number. Okay. So are we still doing okay so far with this stuff? Okay, very good.
Question.
Yeah, go ahead.
Can you explain to me the arithmetic for the 1101 and 001?
Which part again?
Program?
Oh, that one?
Yeah, I'm getting thrown out. So you added first the 1101 and 0010.
You mean this part?
Yeah.
This is for illustrating. Okay, are you having questions about the subtraction itself, or why I have that subtraction there?
The subtraction itself.
The subtraction itself. So we have this row is known as Q in our discussion. This row is known as T because it is a subtraction. If it is an addition, it's known as K.
Okay.
So 1 minus 0 is a 1. That's the R function, right? 1 minus 0 is another one, which is the second R application in a single column. But when you look at B, the borrow of 1 minus 0 is a 0. The borrow of 1 minus 0 is also a 0. So this 0 is 0 or 0 from the first column.
Okay.
Yep.
Got it. Thank you.
Mm-hmm. All right. So are there any additional questions about signed representation? What other things do we know about signed representation? A number plus its own arithmetic negation should be 0. Right? Okay, so let's go ahead and give it a try. Okay, so you guys pick a number and I will use it as for this example. So let me just show you the template first, and then we'll use the template for for this exercise. So you pick anything for x. X itself can be positive, can be negative, it doesn't really matter. And if you add the negation of x, that should get you 0. Okay? So I'm asking you guys to pick a particular bit pattern for x, and then we'll make it work.
Yes, be positive.
Negative 8? Sure. Okay, so negative 8 is good, it's a boundary case. So we'll take negative 8. So negative 8 is represented by 1, 0, 0, 0 as base 2. And we want to add the 2's complement of 1, 0, 0, 0 in base 2 and see whether it equals to 0 or not. So we'll go ahead and carry this thing. So it becomes 1, 0, 0, 0 in base 2 plus the 1's complement of 1, 0, 0, 0 plus 1, because this entire thing is 2's complement. And 1's complement of 1, 0, 0, 0 is 0, 1, 1, 1. And then you add 1 to the whole thing. So you end up with 1, 0, 0, 0 in base 2 plus 1, 0, 0, 0 in base 2. And that turns out to be 0, 0, 0 in base 2, which is 0. That's because we drop the most significant bit. Even though 1, 0, 0, 0 plus 1, 0, 0, 0 is technically 1 followed by 4 zeros, but because when you deal with 2's complement, you limit yourself to only look at a certain number of bits from the least significant bit forward. So that's why we drop that one, because that one is lost entirely. So it does work out. Okay? Are there any questions about this discussion? This went a lot faster than I expected. which is usually a good thing and a bad thing, because the good thing is, yes, we are moving forward, you guys are getting the concept quickly, and the bad thing is, at the back of my mind, I always think, maybe you guys are just not asking the questions. Yes, go ahead.
So, I mean, like you said, why do we care, but are you gonna go over how we do the comparisons and define?
Yep,
for the
that's going to be
user
the
what
next slide, which I haven't really written yet. But since we are already at that point, I can talk about it first, and then I can backfill the notes. Okay, so I might be doing that quite often this semester, because I'm transitioning everything from Moodle onto Canvas. I can always pull the Moodle notes too. But okay, so how do you compare? What is comparison? What is involved when you compare values?
Decide which one's bigger.
You need to decide. Okay, so there are several comparisons. Okay, so very good. So let's take a look at all the different ways of comparing. Can someone list all the comparison operators in C and C++? Okay, so there's less than, greater than, less than or equal to, greater than or equal to, and not equal to. Okay, so those are the 6 given comparison operators in C and C++. So when we talk about this, the very first thing I want to say is you only need one of these. Of the 6 comparison operators, if I give you negation and also conjunction and disjunction, you only need one of these operators. They're like, what? Then why do we have all 6? Well, we have all 6 because programmers are lazy. They don't want to go through the conversion in their mind. So, we just kind of give them all 6. Okay, so if I were to just give you less than, can you re-express all of the other ones using just less than? So let's take a look. X is greater than y if and only if what? Y is less than x. Oh, that's an easy one. We just flip the order. Okay, cool. X is less than or equal to y. Aha, that one is a little bit harder. What do you think that is going to be? If x is less than y, y is not less than x. Remember, you can use logical operators. You can use not, you can use or, you can use and. So this one is just not. It is not the case that y is less than x. Is that okay? Okay, cool. So that makes this one pretty easy too. We just flip the order. Not the case that x is less than y. Okay, all right. Aha, equal to. I mean, that's a stumper. So let's skip equal to first, because not equal to is easier. Not x does not equal to y, but you can only use less than. How are you going to express not equal to? Sorry, go ahead.
You do if it's greater, or if x is greater than y, or if y is, yeah.
Yep, you got it. So how would you write equal to?
If it's
The negation of that, right? The whole negation of x is less than y or y is less than x. Yep. Oh, sorry. Yeah, there you go. Cool.
It's not just laziness. It's too many characters.
Oh, wait until we cannot use negation, conjunction, or disjunction. We have to use NAND for everything. So we should make a new programming language where NAND is the only logical operator and less than is the only comparison operator. Well, you can use macros. I mean, you can just use LE as a macro and re-expand everything to.
Just do it on Bash and
Don't you just like make functions that would be like comparators?
Huh?
You just make huge fun.
Well, in C++,
Three-way
you
functions.
can overload operators.
Yeah, exactly.
Just put it into a library and just
Yeah.
be done.
But so even though it is practically not useful to us, it is still important to know that, hey, if we only know how to compare using less than, we can span all of the other comparisons. Now, why is that still useful? Even though to us it's way too tedious, we don't want to write code like that. But what about the processor? What about the compiler? What is the job of the compiler? It translates code that you write, which has the 6 comparison operators and the 20 gazillion Boolean operators, right? Into something that the processor can understand. Do you think the processor minds tedious stuff like, oh, I can only do AND, or I can only do less than? No, it doesn't care, right? So the compiler's job is to translate something that you can easily write because we understand all of these comparison operators, we understand and or not and stuff like that. As long as the compiler has a systematic way and correct way to translate all of that stuff into the tedious stuff, which is NAND and less than only, what do we care? Right? But what are we buying? I mean, you know, all of this stuff here, why would we intentionally make the low-level operation that the processor can perform as simple as it gets? Is it buying us anything? Why would we want to do something like that? Yep.
We need less circuitry.
Aha, we would end up with a processor that has less circuitry, but it'll be slower, right? You know, because if you think about it, you know, you're breaking up bigger chunks of operation into tedious small chunks of operations, so it would be kind of slower. So even if it were slower, why do we want to still want to do that?
Increase the amount of times you're able to reuse the same part, which I guess is the same thing, but in terms of code. So if you're not using these other codes, you're able to reuse those circuits.
You can reuse the circuit. I like that.
Instead of having circuits that are just being left there that are not being used, which would also make things slower.
Aha, I like that concept. Okay, so we want to improve the utilization of silicon, the transistors. We don't want to leave a whole bunch of transistors on the processor that for the most part, you know, is not utilized. Okay, so we are really looking into RISC versus CISC. So I'm just kind of segueing into something that I did not intend to talk about today, but seems like a good context to start to talk about it. Okay. RISC stands for Reduced Instruction Set Computer. CISC stands for Complex Instruction Set Computer. So the bottom line is, do you want your processor in hardware to be able to do a lot of things per instruction, or do you want it to only be able to do some really basic stuff, but then you can spell out complex operations using multiple instructions?
Depends.
Okay. Sorry?
Depends.
It depends. Okay, so it depends on what? Yep.
Well, my phone is RISC architecture, and that helps save battery life and generate low amounts of heat.
Yes. Uh-huh.
Whereas my PC, I'm not looking to wait hours to generate, you know, a 3D model or something, so I want it to be CISC so that it gets the best IPC it can have.
That's what most people believe. Okay, most people believe that, you know, CISC processors are faster. Now, it depends on how you compare. If you compare a single CISC processor against a single RISC processor, yeah, probably the CISC processor is going to be a little bit faster, not by a whole lot. Okay, but these days, you know, how fast a single processor is no longer important. Okay, so let's look at things from the perspective of Amazon or Google or Pixar, where they have huge, you know, buildings filled with computer hardware because they need to do massive amount of computation. Okay, they're always trying to cram more processing power into these buildings. Okay, because, you know, there's no end to, you know, how much processing power they can actually utilize. What is the limiting factor?
Power.
Space.
Okay, so you're giving X amount of space, so space is constrained already. So what else is going to be the secondary constraint? Even if space is not a problem, this constraint will limit how much processing power you can pack into a building.
Energy, power.
Well, it's related to power. Heat. Very good. Okay, so we have the right answer. So the best way to imagine this is to think about a LAN party. Okay, so let's say somebody here is going to host a LAN party. Okay, you guys like LAN parties, right? So you say, okay, so we have a LAN party, but since you're living in your parents' house, you only have a room. Your parents say, yes, you can have your friends over, but they cannot spill over. Everybody has to be in your room. You're like, okay, fine. Okay. So the first thing you check is the circuit breaker leading to your room has enough juice. Because you don't want everybody to plug in, turn on all the computers, and all the computers shut down because it flipped the circuit breaker. Fine. So you say, okay, can I have a 30 amp breaker just getting to my room? Your parent goes like, are you paying the electrician? Yes. Okay, cool, you can have it. 30 amp breaker. Now 30 amp times 110 volts, that's how you calculate power, is 3 kilowatts. Okay? You go like, 3 kilowatts, that sounds like a lot, but it's not. Who has recently put together a gaming computer, desktop size, with top end everything, including the graphics cards? Okay, so how much power does one graphics card consume?
Depends.
We're talking about the top high end stuff, okay, not the
Up
low
to
end.
200 watts, sometimes a little higher.
I think a little more than that. I think one card can use up to 300 watts.
Is it AMD?
I think it's NVIDIA. I mean, the top end, graphics cards, they
I don't know what the TIs are pulling now. I thought they were still.
Now I have to find out. You guys have piqued my curiosity.
Right?
That is the last thing you want to do in my classes.
1080 for
I think it's a
I
thermal.
mean, GeForce is pretty good, right?
Hmm?
Is it 1080 the most?
Okay, so we want to go to computer components, and then we look at video cards. And we want to look at desktop graphics cards, okay? And probably look at sorted by price.
Yeah,
That's a good one.
That's a good one.
That's a good one. I'm not paying for that. Okay, so you want to look at the thermal specification of this thing.
230 TDP.
Where?
Oh, no, that's from what I remember NVIDIA quoting for their Founders Edition.
Oh, okay.
230 watts.
Well, the specification should be somewhere, right? Specifications. And let's see. It has got, the power connector is 2 by 8 pins. That should tell you something. The graphics card all by itself needs 2 power connectors, each one having 8 pins. I used to design circuit boards, so I know how much current can be drawn from each connector, and needing 2 is a lot. It doesn't quite say.
What's the total amp output of an 8-pin?
Huh?
What's the total amp?
Well, it depends on the size of the pins too, but typically you can pull, at least several amps out of one pin.
And those are 12 volt.
I'm not sure whether it's using 12 volts or not. I'm not sure about the voltage at those pins. Okay, so I can't exactly find the power consumption of this particular chip.
That's a pretty important stat, too.
It is supposed to be pretty
Just buy the
important.
1,000 watt power supply, you'll be fine. Spend more money.
Okay, let's look up the chipset. Where's
NVIDIA
the?
has TDP on their website.
Okay. But this is also supporting SLI, which means you can link several of these things together. So if you want to play your CS:GO, at 500 frames per second, where an octopus cannot differentiate is this real or not, because Octopi actually has a very high refresh rate. So, and flies too, okay? And that's why you can never really catch a fly with your hand, because to a fly, your fastest kung fu move is in slow-mo.
But
they
they
can
always
see
jump out.
they can see your hand approaching, like, oh yeah, it's coming. I'm gonna have one last swap here. Oh, it's still here. Okay, fine, I'm gonna back away a little bit. That's how flies would see it. Because our lights here, these flickering, fluorescent lights, to us, is not flickering. To most people, it's not flickering. But to flies, they can see it's on, off, on, because they have a much higher refresh rate. So to us, any frame rate more than 100 is, we cannot really differentiate. It's only certain animals that can differentiate beyond a certain point. Okay, so getting back to the example. So you have like 2 or 3 of these things that are linked together. So you have a 1,000 watt power supply, just to supply enough juice, right? And you're using almost 100 watt out of that 1 kilowatt power supply.
It's 250.
Huh?
250 watts.
250 watts.
Yeah, for the 1080 Ti.
Okay, so 1 card is 250, and 2 cards would be 500.
And I think you're able to link them up to 16, aren't you?
Which motherboard allows you to link it up to 16, right? So let's say you only have 2 of these, you link it up, 500 watts. Your processor is about another 100, 120 watts or so, and then plus the hard drives and whatnot. So let's call that 750 watts, okay? So your breaker is 30 amp, right? So you have 30 amp breaker, and each computer on the average takes about 750 watts, and you say, we can have 4 of these things in the room. Cool? Yeah? All right? So you have 3,000 watts of computing equipment in the same room. And this is your room, which is not going to be a huge room, so it's going to be 10 by 12-ish, okay? How much power is one hair dryer? About 1.5 kilowatts, okay, 1,500 watts. So it is the same thing as running 2 hair dryers full blown at the hottest setting the whole time. Now we don't really feel that hair dryers is too much of a problem because we only run it for what, 10 minutes at the most. I mean, I don't have long hair. I don't have much hair. Okay, so I don't even use a hair dryer. But for those of you who use a hair dryer, how long do you keep it on?
30 seconds.
30 seconds.
5 minutes at the most.
5 minutes at the most. Okay. How long is one
Plan session?
Yeah.
Depends. 8 to 4 in the morning.
Okay, 8 to 4 in the morning. Very good. So it's long, right? So you're basically keeping 2 hair dryers at full blown on the entire time for 6 hours. That's the amount of heat that you're dumping into the room. How do you get rid of that heat? Okay, there are several ways, right? So there's radiation. So you're waiting for that heat to penetrate the wall, so it will start to radiate to the outside. So that when somebody uses a FLIR device to look at your room, it's glowing in the dark, right?
There's insulation.
And then the DEA show.
And then plus, but most houses have insulation, so you have to open up the window and then use air cooling technique, right?
Open the door.
But I can tell you, you can open the door until your mom screams and you go like, don't let the hot air into the rest of the house. Slam the door and seal it shut too, right? So use aluminum tape, use the HVAC tape to seal your room. And then the rest of you is going to die in that room because it's too hot. The 4 gamers will be dying in the room because it's too hot. That is the problem that data centers are getting into. Okay, it's not how much power they can plumb. It's not the plumbing of the power itself. They can bring plenty of power into the building. They can in fact, put a generator in the middle of the entire facility to power up the whole thing. Google has a license to supply power. They can be a power supplying company if they choose to. Because they saw that they would need a lot of power, might as well have our own generator. That's not a problem. The problem is how quickly you can extract heat from the interior of a building.
Heat sinks.
Solve that and you're a billionaire, right?
Huh?
Solve that and you're a billionaire, right?
Say that
If
one?
you can solve that, you're pretty much like a billionaire. Like, is that the issue right now?
If you solve that problem, then you can pack more processing power into a smaller space. Okay, so, I mean, why would that have anything to do with CISC versus RISC? See, I seem to be distracted and fragmented, but I remember the context. Yeah. So when you look at RISC versus CISC, the measuring unit that favors RISC has to do with how much processing power per joules of energy. Okay, so we are looking at, I don't know, giga instructions per joule. What is this unit in physics?
Joule.
Yep, joule. It's energy. It's energy. It's a unit of energy, or watt second. Okay, 1 watt second is 1 joule. Okay. This is why RISC is winning, because even though they might be slower as a processor, but in terms of how much computation it can perform per unit of energy, they are higher. It's because exactly what you guys mentioned earlier. It has a better utilization of the transistors, as opposed to CISC, where you have a lot of transistors. If you need to, they can do a lot of computations at the same time, but we are not utilizing all the transistors all the time. Yep.
Does that have anything to do with why we want to use the simplest things like less than and and? Yeah.
Yep. Yep.
Those are the reduced. The complex would be like a less than or equals to.
Right, exactly. So the compiler is helping us a lot, because we'll still be writing C programs, whether it's executing on the CISC machine or RISC machine, but the compiler doesn't mind translating our complex specifications into really, really tedious, small, tiny chunks of instructions that will favor RISC. But the CISC is losing because it just generates too much heat. For the same amount of computation, let's say you're inverting a matrix, okay? The CISC processor is going to use more energy. And basically all the energy is turning into heat. Yeah, question?
I was going to say, I heard RISC has, the only downside to RISC is it needs more memory, it needs more space to store its programs because they're so down to the byte simple that it's just drawn out across.
But that is not a problem anymore. It used to be a problem, there used to be a problem of, we cannot fit enough RAM into a system, but that is hardly a problem. So all the downsides of a RISC is pretty much gone, but all the positive parts of RISC is still there. So that's why you find RISC processors in your watch, in your phone, in your tablet, but you also find the same thing in huge, big data centers. So now it really begs the question, why are we still using CISC on your desktop computers?
Backwards compatibility.
Backwards compatibilities, and then if you ask anybody using Linux, they go, what is backward compatibility? You got a new architecture? Fine, we'll retarget GCC first, and then we'll recompile the kernel, rewrite maybe 5% of all the code for the really deep kernel part, and we're done. What is the holdback? Why are we still using CISC processors on the desktop? You guys won't see that in my classes, but you will see in other classes. What is the first thing that I do at the beginning of a class? I reboot the computer. Why did I reboot the computer?
Because you want Linux.
Because I use Linux. So if I don't reboot the computer, I'll be using Windows. And Windows is only available on what platforms?
CISC for right now.
Well, they do have certain RISC platforms, like they have
they're coming out with a new one from,
Windows Phone Edition and stuff like that.
Which they discontinued.
Oh, they have?
They're supporting it, yeah.
Yeah, I just thought that they would discontinue that pretty soon because it's not gaining any momentum at all. Yep.
They just recently debuted a Windows 10 desktop edition running on a Qualcomm 10-core CISC CPU.
CISC CPU or RISC?
Sorry.
RISC CPU.
ARM processor.
On and off, they have tried many times to move their operating system, but why do you think there's a big hesitation for Microsoft to migrate their operating system and applications and everything that they do, the Exchange server and whatnot, onto the RISC platform? Why do you think there's a big hesitation?
Go back to backwards compatibility.
Right, but why do they want that backward compatibility so much that they would strong-arm Intel and say, if you guys stop making backward compatible processors, we are going to do something to you.
Legacy software.
Why is this so important? When the rest of the world goes like, oh, new processor, cool, we'll just retarget the compiler, and then we'll rewrite certain parts of the kernel, recompile everything, it's all cool.
Just live parts.
It's because their compiler is difficult to retarget. That can be the only logical conclusion, is the compiler that they use internally to crank out Windows and all of their applications is somewhat difficult to retarget. The back end is not modular enough where they can just say, oh, we are retargeting a new architecture, easy peasy. We'll send the team, back-end team to rework the compiler, and we'll get it done pretty quickly. That's the only explanation, is their compiler is not written in a modular way. Now, GCC, G++, okay, which is what you use in code blocks and all of the other software that you use in 360, has a very, very modular backend. In other words, the compiling part, which is the syntax part, is entirely separated from the backend part, where you really need to know what processor you're targeting. So if you have a new processor, you're only rewriting a very, very small portion of the compiler, and it will still do all the optimization, all the fancy type checking and whatnot. And as a result, anything that is based on, that's built by GCC or G++, if you retarget the compiler, you can easily just reuse all the existing code and crank out new executable for the new processor. The Linux kernel, for the most part, is written in C, not even C++. Okay, it's mostly written in C, which means recompiling will work for most of the kernel. It's only at the very deepest part of the kernel where you have to deal with threading and all the other stuff that is actually architecture dependent. That has to be written in assembly. But that's a very small portion of the entire operating system.
So what is Windows kernel, NTFS, or whatever, written in, if it's not C?
That's a good question. I'm pretty sure Wikipedia may have some insight over that. I know the original Windows had Pascal code in it, but that's like really, really old. NT itself might be mostly C, but once again, the problem is not just the operating system itself, it's also the compiler. If they cannot retarget the compiler, they cannot reuse the C code they already have. Yep.
It still has Pascal in it.
It still has Pascal in it?
There are parts of Windows that they haven't rewritten since DOS.
That probably would be the front end, the GUI part, because because Windows is misleading. Which part is Windows? Are we referring to the GUI part, or are we talking about the task or process, the scheduling or the threading part? We look at the entire thing as Windows, as opposed to Linux, where Linux is really only limited to the core part. The GUI, what you see here, has a different name. Okay, we have X window, and then on top of that we have XFCE4, which is what I use. But it has a very clean separation between the GUI and the actual core part of the operating system. So one last thing before I leave today is to show you, I've used Debian, and I'm pretty sure all the architectures are similar. So if you look up any package, okay, and just need to find a particular package, Perl, and okay, I'm just going to look for a particular package. Where is it? Okay. It's not letting me. I'm trying to find out, what architecture it is supporting. Okay.
Hardware is supported.
Okay, there we go. Thank you. So of the processors, it is supporting the Intel processor, AMD, Cyrix, Transmeta. It is supporting actually a lot more than that. It's even supporting cisp310, which is a mainframe from IBM back in the really, really good old days. Like we're talking about mainframe days or mini computer days where a computer is about the size of a mini refrigerator. Yeah, even those things are supported. And if you look at top end university research, where people try to experiment with better architecture to support more processing speed and experimenting with hardware supported threading and stuff like that, there will be people designing the hardware, and they can get Linux to work with the proposed hardware that is not even in silicon. So the whole thing the processor is running in an emulator, and then they can run Linux with the emulated processor. They can retarget the operating system in so short of a time that they can have the operating system up and running before they can even have silicon done.
Nice.
So that tells you about the mobility when you're dealing with something that has a back end that is easy to retarget to a new processor. But the point is, there's no place for CISC anymore. There really is no place for CISC. The desktop computers really should be using RISC too. For power efficiency, it should be switching to RISC already. The whole CISC thing is archaic, is due to historical reasons and a strong preference on Microsoft's part. And that's the only reason why we are still using CISC. Yep?
PowerPC back in the day, that's the IBM processor, right?
That's for another class. That's a whole digression for one whole other class.
I was under the impression that it was a RISC processor as well, but it had heat issues back with Mac.
Okay, so we can continue this discussion in the lab.